So, all right, thank you very much for joining the three of you. I'm sorry to hear that some of you were unavailable because of exams and other commitments, but hopefully, you know, you can listen to this webinar when you're doing something else in the background, just to get a feel. Maybe you catch some interest. So this is the second part well, this is the second webinar. Just to remind you, the first webinar, we went over an introduction and some examples. I sent out the slides, and the YouTube link of Professor Kirua, Professor Phil Ansel, and I don't remember who else. I will do the same again, together with the link to the YouTube video. The YouTube video is unlisted, so you need this link to find it. Otherwise, you won't be able to find it, right? I mean, mainly. Anyway, so we went through an introduction. The slides of the introduction are here, and the recording is on the YouTube link. And the second part, basically, Megan just gave some examples of using this aircraft dynamics library. And she went through some details on how we could use this FMI standard in, Modelica and the FMI standard for this kind of project, inspired on similar projects that they're doing in Europe and in the industry, where they use these technologies. So those slides are here, and they are in the link. I will send us a summary of slides with all of the links so that you guys know what to find. But basically, what we cover here is how these two technologies will allow you to go through the model-based development cycle, or the V, for the case of aircraft, generic aircraft applications, and how this fits into the process integration and the side optimization, which some other people also call it MDAO. It has different names, but the idea is that you can have bigger and bigger integration across the different design phases that we have. So we illustrated what we can do up to now with Modelica and the FMI standard. Only Modelica, we can cover these areas of the process. If we add the FMI standard, we could actually use, interact with 3D parameters, integrated RSM for the geometry. So these RSM are the response surface models. This is basically a discretized simplified version of what you actually use. We have not done that ourselves so much, other than the examples that you have seen. But in current projects in elsewhere, they are able to do this whole process. If you want to do optimize, this is possible for simulation, right? But if you want to do optimization of the whole thing, this could be very difficult with this technology. So that's just to give you an overview of how we can, having these models in Modelica, how we can actually build everything in multi-domain, at least at some level of fidelity that will allow us to cover the different design phases. So it's very useful at the beginning of the project that we have something that is rough enough but useful to guide the design process. And that's what we have to do at RPI, is just, you know, try to develop some multi-domain models for an architecture for guidance. That's kind of the idea of part of our research. We are not experts in any other domain than the power systems. We do a little bit power electronics, not really building anything. So after we go through this first phase of the project where we're trying to develop some reduced order models to go through at least part of this, we will just really focus on the power systems design. So basically you can think about, how do we link these requirements from the area structure to deal with propulsion and performance, and how those results can fit into the other design. That's kind of the idea of what we're trying to bring to the table and share with everybody, because this is a multi-engineering and collaborative approach that you need to have to do these big projects. All right, so today what we're gonna cover is Megan is gonna take over today entirely. She will go through some details, and she will also have the models open on her computer for three things that we are doing in CHEETA. Megan, we didn't have the architecture to show them either, right?
Yeah.
Do you have the whole architecture?
Yeah, it's, I think, in the example library still. I might have removed it.
Yeah, it will have been a good idea to cover that, but I guess we can do that at a later stage. Maybe you can make a note so that we can explain people. But anyway, so basically what we here is the order of how we're doing things, right? So we have a simple drone example or a quadrocopter model that we're using to explain basic principles of multi-domain modeling. Primarily, what are interfaces? How do you couple different domains? So, for example, how do you couple the electrical power aspects to mechanical variables? How do you use equations directly without having to derive the block diagrams and other aspects to develop this? And we are using this drone example because we actually have a little test bed where we have the actual drone. So what we want to illustrate is that, developing models can help us represent a multi-domain system, and it can also help us when we are building it to improve the design. So, and finally, at the last stage, based on the Model V development process, so let me open that slide. If you look at this slide, right, at some point we have to verify that these models are actually useful, right? That they represent reality at some level. So for that, we are actually going to have some measurements from our testbed where we're going to try to calibrate our drone models. And this is just to give some insight on how you build multi-domain models that, for example, we were talking with a faculty in aerospace, and he says that our aerospace models are very primitive, and we agree. But the point being is that it's better to have some low order models that include a representation of the system beyond a single parameter of load, for example, of a single requirement, or that is basically extremely crude. It's better to have some sort of representation of the dynamics of the system, so that when we analyze an entire multi-domain system, we can design the controls better. And when you're dealing with electrical power, it's very good to have a better picture of how the dynamics put constraints on how the control responds on the individual components, for example, the converters, and the integrated power system as a whole will have. So in that way, we can actually be able to deliver the performance that you want from the power system to meet the flight maneuver, the steady state, and all the different aspects of flying a plane in a more integrated way. So that's the first part of what the intention with this example. The second one is that as a baseline, right, we start with an existing plane to show how we can use this framework to implement models of an existing system. And here the goal is to illustrate how the use of templates and reconfigurable models will allow us to quickly change control configuration or a whole part of the system to do analysis without having to rebuild everything in different versions. So this will allow us to, based on these templates, for example, we can go and represent a fuel cell with a very simple voltage source, or with a simple left click, we could represent the fuel cell with all the electrochemistry, everything, right? So that's kind of the idea, how we can move between low order representations and higher order representations within the same architecture of the system. Like, these are the pieces, this is how they're connected, but within that architecture, you can change different levels of granularity of what you represent. And finally, based on the recommendation of the power system from Professor Kiruba, we started implementing something using this approach. And that's it. So for now, I'm gonna let Megan take over as a presenter. So let me stop sharing and make her the presenter.
Okay.
And I will be here online on mute. If somebody needs me to clarify some question, just let me know. Yeah, okay, Megan, you can take it away.
Okay. So today we're going to go through some examples using Modelica, and we'll going through how we can do multi-domain models. So first things first, we'll go over a drone example, which is our quadcopter, our Boeing electrical system example, to show how we can use models that we originally developed in Simulink, and be able to implement those again using Dymola, and be able to use templates so we can reuse our models. And then our preliminary electrical system design. We have a model that we got from Karuba's group that we've implemented, we're working on now. So first things first is our drone example, which will show us how to create first order models using multi-domain interfaces. So here is the drone that we have currently at RPI in our testbed, and how we're linking everything together. We have our physical model for our chassis of our drone, our controller, the propellers, our sensors for the GPS and accelerometer. We're linking those all together using different domains. You can see over between the propellers and the drone chassis where it's like a light gray line connecting those two together, which is the mechanical interface. So all of the rotational and translational mechanical equations are stored and connected between those. And then the dark blue lines are the real interfaces, which are routing signals to be sent between components. So starting from the absolute beginning, we can implement our first order models using different equations and parameters. In Modelica, we're able to implement both differential equations and algebraic equations. We don't have to transfer everything over to whatever form to solve implicitly like we do in MATLAB. We can just type it in the way that you would write it out on a piece of paper. So things like Maxwell's equations, these equations to relate the speed with torque and stuff don't need to be transferred over. I showed this example just a couple minutes ago in case you didn't notice and were like zoned out. But down here we can type in our equations, and then we can also view them in mathematical notation by just switching the view. I can show that again if anybody needs it. But what we need is to be able to look at differential and algebraic equations to model every one subsystem's behavior. The parameters that we need to, for first order models, we would need to look at the parameters that would impact the behavior of the system the most. We're eliminating a lot of those higher order equations, and we're only focusing on the low order equations that would most impact the model, and then it would be translated as such over there. We can also make our own interfaces by coupling components using physically meaningful variables. So here we, as I explained before, that light gray line will link together the mechanical components. It contains information with the position, orientation, force, and torque of a component. So we can model how a propeller is moving and different things like that. We can also do this for different things as well. So in an electrical system, we can do voltage and current, linking the components together. I don't know what they would be in other domains, but for the thermal domain, other sorts of domains, we can do this all, which is important to do since we have a bunch of different domains that we need to address within our aircraft. So these domains can all be coupled together within one model as well. They just need to be coupled together like to like. So here, this example is the whole motor system of our aircraft, our drone. So we have our motor, the rotor, and the blades. So we're able to just be able to mix and match what kind of signals that we want to be using within one model. So we're taking in the position vector from whatever real signal, which is coming from a controller, which is computed using a transfer function and different sort of PID controllers and such. That goes into the motor. The motor translates all of those signals into a mechanical signal, into a force and a torque, which gets sent to the rotor, which drives the blades to turn. It also will interface with the airframe to, I think, just give it know where its relative position is. So why we need to do this is we need to know what kind of signals need to be passed between components, and we need to know what kind of variables that we need to couple. Like I said before, we can couple things like in a purely electrical component, we need voltage and current together. In the case of the motor, the electrical variables are coupled through the mechanical variables models equations. And this again shows how we can translate between components themselves. The force component will switch from a real component couple value to a mechanical value to be then connected to the mechanical frame of the drone. So after we have all of this modeled, we can then simulate the system. We set it up where we have everything I showed before, the controller, the rotors and the propellers, the blades, everything's all packaged into this model on the far right, which is the drone. We're putting in a constant value for the X and Y position, which are these top two triangles on the left, and then the bottom triangle is taking in a noisy signal from, well, it's a ramped signal with a little bit of noise to be able to check that our gain constants that we gave our drone are stable. So to be able to, did somebody else just join? I think so. Yep. Bill just joined. Hello. So we need to check our model for syntax errors, unbalanced equations, make sure our system's well posed. Once that check is passed, we can translate our model, which will produce a C code and then for the model and then simulate it. And we can also edit the simulation settings. So let me show that too, how we can do that. So here is our drone model, and let me see, this one's it. So this is just putting in the ideal signal. This is putting in the noisy signal. This shows just the model layer of the thing. We can check our equation, and it'll tell us that everything checks okay. And then this will translate the model. And we can also edit our simulation settings. So the fun thing about this is we have the option to switch between a bunch of different solvers, same thing like Simulink. so we can verify the behavior of our model using different solvers, because different solvers sometimes do different things depending on what kind of algorithm they take and how that will affect the model itself. And then we can press OK and hit this button to simulate. Another thing to note is it also produces a map file of the results of your simulation, so you can export that into MATLAB and be able to do analysis there. So here we just simulated our drone model, and it's also set up for animation, so we can animate it and it goes up and it flies away, which is fun. Yeah, so this is the same thing that I just showed, but in graphical form. So I just showed you all the animation. We can also plot the outputs of that. So let me show that too. So we have our animation that we just showed. We can also go into this tab and choose between different, every different parameter that we have to do whatever, plot whatever we want. So here is like the X axis position, Y-axis position. We can add another plot to show the Z-axis position and compare those to the input, whatever we want. Okay. I think that's it for the drone example. Are there any questions? Okay. So now that we know how to set up our models using different equations and interface for different domains, we want to also...
Sorry, Megan. You went through the slides. Now, can you open Dymola and go through the model?
I did.
Yeah, but you went too fast.
Okay, I can go back through it. There. So this is our drone model. Here's our inputs that we're feeding it. We're feeding it a constant, saying that we're not changing its X and Y axis position. We're only changing the vertical position of the drone. Inside of here, we can open our drone model. Here, we're routing in our X, Y, and Z position. This block just kind of lumps those coordinates together into one array. This is being fed into the controller. The controller's here. We take in our position and the yaw of the controller that goes through a couple different PID blocks. And we also are feeding in a GPS position and a gyroscope position and the height, which is actually coupled to nothing. It needs to be fixed. But the position is then processed and filtered out and sent. Each of these Y positions right here are sent to the propellers, and they're all control one propeller. The propeller takes in that position and signal there, feeds it into the motor, which then controls the rotor and the blades and tells it how to spin, what direction they're spinning in, how much they need to lift and go down by. And then,
so you can notice here for the machines guy, right? You can notice here that our model of the DC motor is very simple, right? Because we are not, it's basically receiving an input of how it has to vary show it, Megan?
Yeah, so this is our DC motor. It's a motor inside of a motor. It is just a simple guy. It's just taking in, what is its input? Current, and it's translating that current into a torque and a force.
So of course, so this is very similar to what a lot of people does to ignore the power converters with you simply have the current commands that the resulting current references, right? It's very similar to that. So in the next stage, what Megan will do to elaborate on this little power system that each propeller has is going to make it more in detail, this part. So you can see that, I mean, as we will have to modify a little bit the interfaces, but we don't have to modify the rest of the model.
Yeah. So we're good on that. We can go on.
To the, no. Go to the upper layer of the model. Where you have the propellers. Okay, so you can show them the model of the rotor and the blades also now.
Yeah, so the rotor is then connected via two torques and then a force driving that. So then we're driving the revolute, which is connecting us to the blade in the airplane or in the airframe there.
And now you can show them the propeller, yeah.
Yep,
Blade, sorry.
the propeller of the model, which is just two body masses. We're giving it the position of the mass and the inertia tensor. We're also, if we wanted to, but I haven't been able to figure it out, we can put in like a CAD file to, yeah, we have the option here to put in our own CAD file of a custom part if we wanted to customize the blade or really any sort of physical component of the drone.
Yeah, and this allows to do a little bit better representation graphically, right? But the way that we're modeling these parts, then going back at the beginning of the discussion for this webinar, was that we are doing basically multi-body simulation for the mechanical part. So our blades are simply a very simple representation. So we're not taking into account the geometry of the blades in detail, right? The geometry of the blades can have a big influence on the aerodynamic performance. But this is better than just having nothing, okay? So this will at least have the kinematic dynamics, the Newtonian dynamics for this multi-body system. So whatever the torque delivered to the motor to be able to move these lump masses is going to be a better representation than having just a fixed value, for example, or a table. Because if you have a table of values, you can't really capture any dynamics of that. So this is a simplified way of representing this, right? And this is the idea with starting with very low order models. This can be enhanced. So Megan, can you open your Chrome?
Yeah.
And type flexible bodies library.
This one.
Yeah, you can click there. Maybe. So this is a library that will allow you to, if you wanted to, yeah. So you see, you could actually go now and if you, I think there's example for a helicopter blade. It will allow you to parameterize a finite element type method equivalent. So yeah, you see there's the blades.
Yeah.
So these are discretized PDE models that you can read from Abacus, I think, if you wanted to add more of the details in the mechanical part. Okay, so we're not doing that right now, but you know, if you wanted to go and do more detailed things to model the blades, it is possible to do it, just in case you had a question about those things. And we haven't done that ourselves because, of course, we are not mechanical engineers. But I just want you to know that there is the possibility of doing this kind of things. Just go ahead.
And I was just going to add. So I know that this is kind of a toy problem or a specific example. And by the way, sorry for joining so late. I had a meeting that went over. But if for kind of future work stuff, if you're ever interested in adding kind of more higher level aero modeling, there are some aerodynamic torques that, for instance, can be imparted due to different interactions with the blades. That's something that actually we know how to do. And so that might be a feature that could be added in like future iterations or whatever. I know that's not the focus of this, so I'll shut up, but I just thought I'd throw that out there.
No, but Phil, remember that, I mean, at least what I think, since this is a notional aircraft, right? And we're trying to, with this task that we have, we're trying to kind of communicate of the need for doing a bringing into the design phase more interaction between the different domains, right? We might, so if you would like to take that as part of the project that we do it to illustrate and communicate to NASA and the other project partners that, you know, there is a possibility now to somehow start bringing into the design process more aspects. So at the end for us, these representations are going to help us develop our power system better and the controls than not having anything. So if you want to do that, that's something that as long as you think it's good to illustrate, we can discuss further. It's
yeah. I'm sorry, I shouldn't have said anything. I guess I didn't want to give the impression that it wasn't an expectation. It was just hey, if you see this going places and you'd like to tag team outside of the scope even of, you know, the ULI, for instance, if you're looking for ways of including, and which, by the way, I am sitting on some data for, or some information for modeling of ducted fan dynamics that I'm going to distill and ship out to you. I just haven't had a chance to do so yet. You know, to give you something else to munch on.
Yeah, I think Megan will be interested, so we can have a follow-up about that.
Yeah, great. Anyway, I'll stop talking now.
No, that's the goal of the call, Phil, that if you have any questions or ideas, you put it on the table and we see what we can do. Megan, go back to the model so we can, I just want to go over a few more things. If you go to the top layer, right?
Okay.
Okay.
This top layer is the other top layer.
So the next thing that you could explain is that we are connecting to the airframe, right?
Yep.
So you could now show the airframe model.
So we're now connecting to the airframe model, which is here inside of this model. Here is the connection on the left, airframe A1, airframe A2, and so on are all the connections to the propellers. And this right here is the connection to the controller. So each of these is a mast for one of the wings of the drone that's like holding the propeller on the end.
The axis, right?
Yeah. And then here's the center of the controller that holds, or the drone that holds the controller and the battery and everything in here. So we just center that at the middle of the system. Okay. I think that's pretty much it for this model.
Okay.
Okay.
Yeah, I just wanted to go in more detail so that since it's a simple example, it's easier to understand the methodology, right?
Yeah. Okay.
Sorry, interruption.
Okay. So going back to, let me get back to my spot. Okay, going back to where we were. So now that we've made our simple model with just first order equations, or we can go up higher to higher orders than that, we also want to make reconfigurable models to be able to demonstrate varying degrees of complexity. So I don't know what different degrees of complexity is for like every domain out there, but for like a motor, for example, we can just model, which I have the example in a minute, but we can just model the simple electrical motor, which would be like in a reactance and driving an EMF. And that's your first simple motor. And then you can move up to different degrees of complexity when you add in all the different higher order equations to model the linking between inductances within the motor and so on. We can do the same thing with transmission lines and other electrical components. So we'll show that. So we want to be able to make efficient models. So we have a hierarchical structure so that we can reuse the model on different levels, reuse different components, subsystems, and so on. And we want to be able to inherit different properties within those models so we can keep reusing them. And the way we're going to do this is by implementing templates. So we can have just a template where you can click on one component and switch between different models there. So the way this is done is we have here the electrical system for Boeing 747. We have the interface, which just acts as a placeholder for that component. So this on the left-hand side is the template. And we have the placeholder for an AC load, 2 DC loads, and a generator. And they are just connected together and used as a template. And when we click on each of those components, we have the option to move between different components to place into the template. So we can put in the induction motor, or permanent magnet synchronous motor, a pump, to switch between different kind of generators. And using the template, we can have variant models and maintenance, which is pretty straightforward from there. So the way that we would do this is we would just say that the model is replaceable, and we could redeclare the models from there. So yeah, this slide shows a better thing. So in Modelico, we can say we have our replaceable green model here, which we can then swap out for other models. So we would like say that we want to redeclare the green model here to use this red model. So we'll switch to have the properties of that and be able to interface with that component model. And then we would want to switch this yellow model out for the green model. And then it would, in a template, it would inherit those properties and keep going from there. So we would be able to, instead of creating a new model, we can just keep reusing it by redeclaring components, which is going to be really helpful in CHEETA since we want to switch between first order models and move all the way up to higher order models. And it'll allow us to be able to analyze the model on different timescales, be able to see super fast transients in the model, as well as be able to just get a general idea when we don't want to simulate some super complex models. Yeah, so the way we do this is we can right click on the component and it'll give us some different options. So let me pull that up, this model up. So here I have some examples. We have our distribution system template. So for an AC load, we can go here, click on change class, and it'll give us all of the matching choices for that. It's freezing. Okay, because it's freezing, I have a screenshot of it. But when we right click, we can go to all matching choices and it will come up with all of the different components that we can use to substitute into that template to simulate. So we have here, it is recognizing that we can put in a couple different DC load models as well as an induction motor to be replaced into that component for simulation. So we want to use this because we want to switch between different degrees of complexity. So like before, I said that we can model a motor to have just a reactance and driving an EMF. So this is just a simple motor model where we have our transfer resistance losses, our reactance losses, some hysteresis, and going in parallel to our EMF. So we have some of the basic losses modeled there, but we don't have all of the dynamic behavior of the generator modeled in this motor. But we can also move up to different degrees of complexity and implement something like a squirrel cage induction motor, going up to higher order models. And we would just do this by defining this component as replaceable, and we can switch between these two components easily by doing the same thing as before, where we want to just change the class and add in a new component. So we want to do this so we can switch between different operation modes and levels of complexity. So, oh, great. This is just closed. Let me open it back up. One second. So opening back up our old model that I just showed before for the 747 system, we can simulate it and show. Let me have it finish loading. So simulating it for having the induction motor, 2 pumps, and why does that not want to work? Because its other library is not loaded. 1 second. Okay. Now we should be good. So right now we have an induction motor, a pump, and a permanent magnet synchronous motor attached to this. Inside of here, we have our generator. We have the controller for the generator, an electrically excited synchronous motor. We're feeding in a reference feed. So I guess I can start here to explain. So we have just a generic IEEE controller driving our motor based off of the output of the motor, the speed, what kind of voltage it's putting out. And this is being sent to a induction motor, which is just taken from the Medelica library, and is driving a pump. And we have another pump here. So we're taking in our AC signal, using a transformer to step down and drive another fuel pump load. And then we have also a permanent magnet synchronous machine over here. We have our speed controller that we designed and all of that stuff. So we simulated our model on, I think, the time scale of like 1 second. Yeah. So we can look at the outputs. I want to look at the output of the generator, and see, we can plot the output voltage. We have our 3 phases offset by 120 degrees. And that's pretty much all we could want to show there. But we can select from different parameters on the side. But the main takeaway from this is that we can switch between different components. It just crashed Dymola when I did. Are there any questions off of that? Okay, we'll keep going. So the final example we were going to show is the preliminary CHEETA electrical system. Karuba's group came up with the parameters for that. So we've been kind of working on implementing just the first order models and moving up from there. We're also going to re-implement this system to focus only on the DC side to be implemented into the drone model that we showed before. So this is the notional system for CHEETA. For here, I didn't implement all of this whole system because it's the same thing copy pasted a bunch of times over. So we're only going to focus on one branch of the fan and the motor, the HTS cable, and our fuel cell. So we're using just the simplest components here. We're going to have to do some model reduction and stuff to get more complex second order, third order behavior for things like the fuel cell. But we haven't gotten to that point yet. So how does this whole system that we showed before translate into Dymola? Here we have our battery / fuel cell. It's just modeled as a simple, I'll pull it up. Actually, okay. Yeah, so this is it with different levels of complexity, but we have, here we have a simple fuel cell, which is modeling the lowest order behavior we can have in a fuel cell. So we have our DC voltage that we want to supply it, plus some simple losses modeled that's feeding into a DC-DC controller to boost the power back up to, or boost the voltage back up to where we want it at that bus. So this is just a simple, this is a step up DC-DC converter that we took from the Medelica standard library. We just modeled our HTS cables as the simplest model that you can have as a transmission line, but we're in the process now that we have models that people did for their course projects in our CPS course, we can put in higher order and more complex models to be able to model the cryogenic behavior that we would see in the HTS cables. So we just use an inductor at first, but we can also add in the pilot line model, which I have in there, but I don't have shown right now. And then we go back to an inverter, which is just a simple DC-AC inverter model. We can also switch this model to have feed into three-phase. We're just having it feeding into a single-phase motor right now. And then we have our motor model. So our motor model is just everything I explained before, but we can go up to more complex models. So this is just with a simple machine. We move up to a average model, so we don't model the switching. We just use averaged components instead of switching, or we can also implement this system to use an induction motor. So it's all the same thing as I showed before, but instead we move up to a more complex motor model where we feed an induction motor the output from the inverter and use that instead, which will allow us to look at the system response in greater detail. So this is everything I had explained before. We've got this whole model, it translates into Dymola. What kind of
I have a quick question. It's really cool what you were able to do with putting together even just a simple fuel cell model. In the converters, so the DC-DC and the inverter, the DC-AC, what role does the PWM signal input have? Can you explain? You might have covered this before, but how is that determined, and what does that do in that conversion process?
So in this inverter model, this is just a basic inverter, like the standardized inverter model. Here we have transistors which are driven.
Wait, Megan, we have to explain a little high level before you go into details.
Okay.
So go back to the picture. Remember, Phil is not an electrical power electronics engineer, so we have to start.
I don't know how inverters work. I'm sorry. There's transformers in it or something. I don't know.
No.
So let me explain. And there's a reason we don't have a transformer right now here, because in this model, the fuel cell output voltage is gonna be at normal operating conditions, right? The voltage of the fuel cell is always gonna be lower than what the voltage that your rest of the system here, in the middle, right? It's rated for. Okay, so you have in here. We wanted to neglect losses to start. So you see, we only have some inductors to represent the cables that you have connected between the DC to DC converter to the inverter. Of course, this is very simplified. We need to have there at least a pi equivalent, for example, that is a resistor.
Yeah, so we can move up to, oh wait, I can show that. We have also models for like a pi equivalent. So instead of just using the motor or the inductor, we can use an inductor, a resistance, and capacitors to provide charging inside a building.
So let's go one step up again. So the goal is to move the energy from the fuel cell to the motor, right? And to enable to do that, we have to pump up the DC voltage of the fuel cell to the rated voltage. So we have a DC to DC converter that will do that. Now, in order to do that, all the power electronic systems that you have need to have their own controller that tells the switches that Megan was showing you, all the transistors, when to turn on and when to turn off. So right now, what we have here, if you look inside of that PWM block, is a very, very simple control model that, that generates, so here, you basically give something called the duty cycle. So that's the rate of change that you want to be turned on and off. And the output you see in magenta, that's going to be the on and off signals that we're sending out. The sawtooth signal of that PWM is going to be our reference that is going to be compared to the part on top to the side on the switching. So power electronic people will look at this and would say it's a joke because it's too simplified. But this is in order to have just to be able to simulate a simple system in steady state operating conditions. So go back to the top. So you see, those PWM models are going to allow us to control the voltage on the right-hand side to the level that we desire. Okay?
So the PWMs are driving the switching process of the power electronics, is that right?
Exactly. And it requires to have some sort of a control functionality on top. So right now we don't have that. The control functionality that you need on top of this is a DC voltage controller that would be controlling the voltage on the DC side where we're connecting to the inductors, because we cannot, the fuel cell voltage is going to be controlled internally by another subsystem. But we need to control the voltage that is on the side of the, we're going to have some cables before we arrive to the inverter, for example. So we have in this very simple thing, we're gonna have a DC network that is these lines, that is very simple, but we need to pump up the voltage. So once you move have that voltage at that level, you can transfer the energy in terms of you can transfer the electrical power between the DC to DC converter, but this is DC power. So you have to convert the DC power into AC power because the motor is going to usually be an AC motor.
Right.
Okay. So the inverter in this side, the PWM is going to be used to be able to go from DC to AC. Okay. And it will also need some control functions. That PWM block is very simple. And finally, we don't have it here because we have a very simple model of the motor. But if we have a correct model of the motor, that motor will also need a variable speed drive controller that does a similar function that the PWM. And finally, all of those individual controllers that you will have, this PWM, the PWM1, and the other one, imagine that they will be expanded to have the control functionalities they need, and that the motor has another controller. Then the energy management system has to tell them what is the references, for example, of the DC voltage, what is the, on the inverter, is going to tell it what is the power that needs to be delivered according to the flight controls.
So then that would mean that the PWMs, in this case the PWMs, but the controllers to those would need to talk to each other too, is that right?
No, that depends.
No, okay, sorry.
No, sorry. That is entirely dependent on the control hierarchy that we want to make. So typically, in this kind of systems, you have a two-layer control, 2 or even 3-layer control hierarchy. Okay, the 3-layer control hierarchy starts at your flight controls, then it goes to the energy management system, and then the energy management system sets the reference points for the distributed controllers at each of the devices.
I see. Okay.
So this is the way that you pass from a change on let's say move from X 10 meters to 20 meters, right? and you're making the joystick move in that direction, you will have to pass those references all the way down there so that that motor can deliver the actual torque.
Got it. Okay,
so,
thanks.
So that is all the energy management control hierarchy that needs to be developed. So what we're doing here is that we're starting at the bottom, and then we need to bring in all of those extra aspects into it.
Great.
Does that help?
Yeah, absolutely. That really does. Sorry for being such a neophyte when it comes to power electronics and controls, but that makes sense.
Don't apologize, Phil. We were lecturing our aerospace professor about how crappy our models are for the.
Oh, I was so proud of them, and they're like, they're not anything.
Well, that's where we can compliment each other.
Yeah, we are all learning in the project, so it's we're happy that you find this interesting at least.
Yeah, absolutely.
Yeah,
all right.
You can continue. I don't remember what you were explaining.
I was beginning to explain how an inverter worked.
No, before that.
Oh. Yeah. So now that we know how the whole model works, we have different domains that we are interfacing with in this model. So in this model, we're specifically just looking at the electrical domain, the Boolean domain, and the mechanical domain.
The Boolean domain doesn't exist. That's just
It's a pulse width modulation, but like
those are switching signals. So I'm gonna go and fix that for you.
Okay, thank you. Okay, so the electrical domain pertains to everything on the side of the model. So ignoring the yeah, this one's good. So ignoring everything from pretty much. Oh, and this one will also show the real domain to have this sensor connect to it. So ignoring everything from basically the inverter to the right, we're just looking at here, and we're only dealing with the electrical domain. Everything from here is just voltage and current being sent between components, basically. And then on the right side, we have, when we're moving up to a more complex motor model, we'll have a sensor reading into our induction motor model and being able to provide a signal voltage for that. And that will produce a mechanical signal to drive our fan. But in the more simple motor system, we will have just the inverter directly electrically connecting to the motor. And inside of the motor, we will move to the mechanical domain via using an EMF. And the EMF will then drive the fan itself. So, yeah. So going back to what we had back in the drone.
Just one intervention. So this is the model that was proposed by Kiruba for the simplified model proposed by Kiruba for these motors. So you see, it was very simple to implement this kind of model using the Modelica standard library because all of these components were available. So we didn't really have to implement any of them ourselves like we do for other things.
And this is just kind of going off the same ideology of before with the drone model, that we want to start with the simple list model that we can have to represent a system, so we can verify the behavior works and that we're on the right track, and then move up to a more complex model. So for the fuel cell, we have our first order model here. We're just modeling it as a positive, negative difference between what sort of DC voltage we want to get. We have some we have some reactance losses here, and then that's going to just feed into the system. And then for our other first order models, we've got a fan. We're inputting our mechanical signal from the motor. And then we have, it's modeled as a rotating disc with an inertia attached, which I'm Not actually sure is right, but nobody's corrected me, so it mechanically makes the most sense to me. And another thing to note we can do is we can propagate these parameters from these models to reach a higher level of declaration. So from the here, from this level, we can then declare the moment of inertia of the fan blades as well as the fixed rotation of the flange of the fan itself from the system level, and it will declare that at lower level components, which is helpful. So when we simulate it, this is the results when I used the average system models, and it's producing the sinusoidal result because of we're driving a sinusoidal result or a sinusoidal wave into the averaged half bridge model there. Yeah, so that's pretty much it with this model. Does anybody have any more questions?
Nobody has any questions? Don't be shy.
Not I this time.
Okay.
Let me have control over the. I can do it myself.
Okay.
So let me then go over finally to the previous slides, what we covered through these two webinars.
I have a question.
Yes, go ahead.
Are we going to increase the fidelity of the model that was simplified just for the simulation at present? Or are we just going to go with the simplified model?
Well, for the entire aircraft, the idea is to do low order models, but we need to improve these low order models. So they're still not the level that they should be, at least. Okay. So yes, but we have to figure out with Phil for the power system. We have to go in full details for all the electrical part, but other parts might just stay in very low order depending on what direction we're going to take.
Okay.
So it kind of depends on where. Once we have one model that kind of abstracts the low order dynamics of each of the parts, we can start going in. Well, even now with some, as we're doing, we're expanding we're working on the power system part in more detail, and it will continue to evolve. But the other parts, for example, the cryogenic cooling and things like that, that might be a very simple thermal network with cooling, for example. I believe I have shown some of those examples in the first session. Yeah. So, for example, here you have an electrical motor that is connected to a mechanical load, and the electrical motor has heating. You can compute the aggregate heating on the component. And here you have the ambient temperature over here. And this circuit here is the thermal network for that motor. So for that component, we can establish a thermal network model. Okay. And at the bottom, you see here, this is the cooling circuit that is going to cool the thermal network and is going to change the temperature on the motor. So this is probably as far as we perceive. So the power system, probably all of them will have to have some sort of simplified thermal representation, all the components of this type. We should have some simplified representation for the cryogenic cooling also, maybe of this type or maybe a little bit more complex. But that's the idea for the multi-domain model, that is lowered enough that it's informative for explaining the challenges of, trying to take into account all the domains during the design process. But like we will zoom in more into the electrical part. At least that's what we plan to do with at RPI. That's what we need to do according to the project, right? But one of the reasons that we're having these webinars is because perhaps others would like to. Well, we need the help from others to get some low order models from different components. So at least they can understand how we put in things into this environment and how do we build the multi-domain system so they can provide us the right information. And second, the other point would be if somebody in the other teams wants to actually go and build them themselves with higher degree of complexity, well, we need to assist them. Who was asking? Abjit, yeah. So that's kind of part of what you need to do. You need to, once you start with in the project, you'll start helping other people to integrate these things together. While Megan and you go into more details of the electrical part, electrical power.
I got a question really quick.
Yes, go ahead.
So you said that FMI was going to be used to integrate like the arrow and geometry stuff into here. Because I noticed that Modelica doesn't have the option for arrow.
Yeah, well, we didn't say that we have to do it. So we covered these slides in the previous lecture. This is the potential uses that we could have depending on what you want to do, right? So one way of integrating the arrow part, according to this N2 diagram, right, would be to be able to supply a better description of the arrow dynamic model. So there is different approaches to do that. We show how we could do that in terms of geometry, and I don't know if we described the other one with an example. It could be in the recording. So there is some low order fidelity models for, but yeah, I would say like low order models for the geometry and the arrow part, even the structures in the aircraft dynamics library. So that's one approach to do that. The other approach, as you were mentioning, so we could do what we are planning to do for this project. Probably is going to be up to here somehow for the part that we're doing at RPI, right? The propulsion is fully electrical, right? So. So if we wanted to bring this arrow part or more of the structures, we have two options. One option is that we do it entirely with the aircraft dynamics library, and that will be a rough approximation. And the other one, let me fix these things that I modified because this is more generic. And the other one would be to use the FMI standard, right? And to use the FMI standard in this case, basically, before we use the FMI standard, the approach to do the inclusion of the aerodynamics is with these response surface models. So that's what we could integrate more easily. Now with the FMI standard, what we can do, going back to my original slides from the first day, the FMI standard, what allows you to do is you can very easily export your Modelica model into other tools, okay? Some tools also allow to export models into Modelica tools or into other tools, okay? So depending on the approach that we use, the one that we prefer to use usually is called model exchange. So we could have here Dymola, the tool that we're using that has all of the models that we have, and we import one of the parts that you have that contains the model, and then Dymola solves it. This is not co-simulation, but it's basically everything being solved by reading these models in FMU form. Now, for the other option is with co-simulation, and if you're interested, I can I give a whole lecture about this, so I can share you the slides about this kind of things. So there's different approaches that we can take depending on what you would like to do. Did that answer the question or just made it worse?
No, that helps a lot. Thank you.
Could you, so if you go to this webpage called fmi-standard.org, you can go into tools. And in here, I mean, the main reason, so I always like to explain this page here for people that have not seen it, right? The legend is important, and the numbers here also are important. So the numbers 1.0 and 2.0 means the version of the standard, okay? Right now, most of the support is coming in form of version 2, and version 3 is being developed, which probably is going to be released next year. And also the tool vendors then, when that is released, will have access to what is called the specification here, but they're also the software development kit, so that they can integrate the FMU standard to be able to read or even export the FMU models. But that's, I'm not sure of the, what is it called, the roadmap right now for that, but in March, I recall that FMI 3 is going to be released next year, somewhere in March. So all of these Modelica models that we have, one thing that we do routinely is that we use them in Python. We use them in Simulink, and there are many tools to do that. So for example, I don't know if you like to use LabVIEW. So LabVIEW only has support for FMI version 1 right now. Okay, so that's not that great. But if you use what's CHEETA, so CHEETA has full support for it, you see? I don't know, if you tell me one name of one tool, I can search it.
What about like Creo?
I don't think that's there.
I don't have that. Okay, gotcha.
No, MATLAB is the most common one, right?
Yeah.
So there's 3 different tools that provide you support to import it. Third-party tools and MATLAB, you know, so the MathWorks doesn't want people to use anything that is not being done in Simulink, but in 2017, they finally gave in and integrated after the car manufacturers told them that we have had enough. We want to be able to use our FMUs there without third-party support. But there is 3 tools that we use. The FMI toolbox from Modelon. It's a third-party tool that requires a license. But there is also the FMPy. Sorry. If you go to GitHub, sorry about that. The other one is called FMI Kit, which is fully open source. Is developed by Dassault Systems. And this gives you more or less the same functionalities. It also allows you to generate FMUs to use in Modelica. So if you go into Simulink and you develop your model, you can use this tool to generate the FMUs to use in another tool, for example. So yeah, so just going back at your question, you have to be very careful, right, with the tools. The main reason that we use Dymola is because we are, so just let me show you. This has full coverage for everything. So the cross-check pass, that is a service that is running online, that is a third party checking that the claim here that it's supporting FMU exports, so you can export your models, or FMU import for each of the different variables is supported. So if it's in green, it's a third party that is checking that. If it's in blue, it's the vendor of the tool, it tells you it works. And if it's like this, it means that they are starting to use it. One of the tools that I remember they use a lot in the Boeing is EC5. So if you see that has a little bit, they claim that they support everything for version 2, right? But you don't know that nobody has checked that. But so you have to test it yourself, basically. The green ones are good because then you know that somebody else checked, right? Yeah.
So Luigi, this also brings up a good point about one other thing too. You mentioned kind of in the scope of what your group is doing, and kind of how Aero is outside of that, which I agree with. And one of the reasons I agree with that is you mentioned about use of different toolboxes that perhaps could be leveraged to facilitate those modeling approaches. But we also actually have a flight performance code that can do, and I kind of hinted at this before, different drag buildup of the aircraft, and with the configuration preset, of this is how big the wing is, this is how big the fuselage is. We can do estimates of what the aircraft lift and drag, what that is, and that is actually already written in Simulink. So I think if we were able to simply kind of make sure that it's up to, spec when it comes to double checking everything and all the connections, we might be able to generate through the FMI toolbox some common code that we can then start using Dymola to represent some of those things in our performance simulations, which will happen later down the road. Or we could have that integrated with your stuff too, if you want.
It can go either direction. It just requires a little bit of care when doing that. I can give a class on that if you want me to. I need to expand the materials because my materials are made not to do something so complicated. But yeah, so if you use that tool, this open source tool, for example, or the FMI toolbox from Modelon, both of those tools allow you to export a model as an FMU to be used anywhere else you want, not just Dymola. You can use it in Python, for example, for scripting and so on. Yeah, we can run the models in Dymola if we export them that way, or we can export our models so that you can use them in Simulink. So maybe I can show you an example from just to make it clear. Show you that then. So, and then let me go and show you the homework maybe. I'm not sure if I have I might have part of it here. So just a little bit more on the FMI since there's some interest. This really came out of the automotive industry. It was an industry-led project called ACOSAT, which is for to be able to do integrated system design for vehicles, for cars, right? So the problem that they had in the past is that each of these suppliers had their own models, and a company like BMW was not able to simulate everything with a single tool. So the solution that they came up with is to create the FMI standard in which each supplier should be able to export their models provided to the integrator in FMI and be able to do the entire system design together and provide input on the specific components to the suppliers and be able to improve the design early on in the design process. I mentioned some of these things. This would take me a whole hour in the details. So Dymola can be used to import FMUs and run them. So here's some example of things that we have done. This is the same model. So we did everything in Dymola first, and then we imported the models into Simulink, you see. There is some difficulties when it comes to the tools that you use. They might create some initialization issues that you don't see in Dymola, but those are just the cost of being able to do those things, right? So let me just show you finally. So here's a very simple example where I'm just using the inbuilt tool. So Simulink only allows, by default with any third-party toolbox, it only allows you to import because they don't want you to export any models. So this is an example how we import a model and run it. So it's quite straightforward. And this is a similar experiment done with the FMI toolbox, which has more richness to it. I think to show you a more detailed example, I will have to show you my class notes. But not sure if I should continue or should I stop.
That's okay. I think we can tackle this later whenever it becomes more relevant, because we're, I think, not at the point yet where we can really do that level of integration between what we already have in the aircraft system and what comes next with the rest of the airplane.
Okay, all right. So, but that, yeah. So here is an example of a model of a Futura pendulum that is very typical in controls. It shows you how we import it, how you have to be careful when running it with the solvers and so on. And here you can see that basically at the end, when you import your FMU into Simulink, you can just put the input and outputs and manipulate it like any Simulink model. Right. So here, this little exercise that I give my students is to design a controller to stabilize the pendulum when you inject some steps into it. Yeah. Is there any other questions? Okay, if there's no other questions, let me just go one more time through the, just to make a summary. I think the best slide to use here is this one. So what Modelica and the FMI standard will allow you to do then is to develop multi-domain models that you can use across this Model B design process. And the models can start very, very simple to do all the requirement study, and then can be you can have simplified models that you can evaluate the different type of architectures for each of the subsystems, and then you can start going in and further increasing the level of detail of one or many of the subsystems. For example, for control design, or for, well, in power, this is important for the power electronic controls especially. And at some point, you can even integrate software into it. So for example, if you have a piece of C code that needs to be integrated, which has the controller specifically, you can use the FMI standard for that, or you can do it directly with C code. So Modelica can allow you to go all the way to through the entire, and Modelica and FMI can allow you to go through the entire chain with some limitations with respect to the aerodynamic part. Okay, so that's, the technology is not there yet to do everything together for the MADO or MDAO or PIRO process, but it can cover a vast array of the design process. And let me go then back to the slides for today, or the overall slides. So just to recap, in the first day, I gave you an introduction on just talking a little bit about general concepts of modeling and simulation, the Modelica and FMI, which are open access standards, so they're supported by multiple tools, and how they can use for what is the characteristic of the standards in general, and why are they useful. And I also showed you the industry adoption. Most relevant for us, at least, and for this project, is this slide. Last year, Boeing announced that they have signed a 30-year contract with Dassault Systems for the 3D Experience platform. The 3D Experience platform, one of the components of it for system level design is what they call Dymola behavioral modeling. So the interface that you're looking at today looks a little bit different than what you have in this platform, but it's essentially Dymola. The graphical interface is just based on a web browser, so it's a little bit different. They also include the CFD and the FEM analysis using CATIA in that part and other tools. I don't have experience on that part, to be honest, but this is why I think it's quite relevant for our project that, you know, Boeing is going to be 30 years with this system, so we can at least provide them some students that know this stuff. So that was the first day. Then we covered these slides on the potential applications, the scope that we could cover using these standards. Is not necessarily everything that we need to do. It's just to give you a perspective of why this is useful. And then Megan covered during the first day, he showed several examples that are included in the aircraft dynamics. That was more or less dedicated for field students to just, you know, get an idea of what's available, what we have available for what Megan is using as a starting point to build the integrated system model. We started with a very simplified notional architecture, and now we're moving into bringing the architecture into this library. So because it's much richer that we can do from scratch. And today, the idea was to dig down into some examples that we are doing in CHEETA. I mean, I could show you hundreds of examples that we've done in the classes and in other projects, but we wanted to show you this little demonstration example for multi-domain model and explain what are interfaces, equation-based modeling. And we implemented the electrical system for the 747 as a baseline of how you do the electrical part of an existing plane, so that we know how it is, right? And how that can be evaluated on different variants of the power system. So modifying the controllers, modifying the kind of model of the machines. And finally, the beginning steps that we are doing to implement the Notional power system model that Professor Hiruma proposed. So I have recorded this webinar. I will add send to Phil. I will send to Phil the slides that Megan presented together with just these two slides with all of the links to the YouTube videos. As I said, the YouTube videos right now are unlisted. If it makes it easier for everybody to put them listed, I don't see a problem with that. We can do it. So I will include the link here for this webinar and for the slides. So I will share these three slides as like an overview of what we are presented, and you can access all the slides through the links so that it's easier to go through it. So if there's no further questions, hello? Is there anybody left? Because I can't see it anymore.
We're still here.
Okay, nobody else has any questions? Okay, so before you guys sign out, Megan, maybe you can take a screenshot of the participants, or I have done it now, so we can maybe prepare a report of the, or just a couple. Maybe you can prepare a couple of slides with this agenda that I'm making, and some the list of people that attended this thing, so that Phil has something to report to our funders.
Yeah, that'd be great. And thanks so much, Megan, and thanks, Luigi, for educating us. This has been very informative.
As long as you're happy, Phil, we're all happy.
As long as NASA's happy, then I'm happy.
Aren't we all?
Thank you very much, everybody. Happy holidays. And let us know if you need any further information. I have discussed with Professor Phil, Professor Haran. There's another couple of professors that I haven't discussed this with at Illinois, but please share it. All of this, please share it with everybody you can at Illinois and the other universities. Maybe Phil, you can send out an email to everybody with the materials, and they can inspect it at their when they're available if they want to. And I mean, again, our idea with the work that we have to do, we really don't want to impose any tool or anything to anybody. So if you just want to give us the model, a simplified model with the parameters, that's fine. We will implement it. We already did that for this simple thing. But if you want to learn, I mean, that's the value of these collaborative models. I mean, we should find a way to support you. So you can discuss with all the faculty in Illinois. I have in the past offered a 1-week course on this Modelica stuff, and I will be happy to do that again if there is enough interest. And so you can discuss that with the other faculty, Phil.
Yeah, that sounds great.
Okay, happy holidays, everybody. Thank you.
Thank you so much. Happy holidays.
Thanks so much.
Happy holidays.
Bye-bye.